Hi, I'm a PhD student from the Stockholm University, and I will talk a little bit about the results from two papers that I did during my PhD that both look into TeV gamma rays from lasers as either a source, a way to constrain new physics, or maybe something that can give us a hint of physics. Jeff?
Yeah,
Okay.
And you can change yes in the arrow.
Okay.
For the pointer.
Okay. So what are blazars? Blazars are one of the most powerful TeV sources in the universe. They are a type of active galactic nuclei, or AGN, which means that they are highly luminous galactic centers that emit the higher than normal luminosity in at least one region of the electromagnetic spectrum. About 10% of these active galactic nuclei have jets, which are beams of ionized matter and radiation that are emitted along the axis of rotation. You can see an example of that here, or Centaurus A, or these two beings that are emitted out. These jets are very strong magnetic fields. And then for about 10% of these jetted AGN, the jets are pointing directly towards the Earth, and in that case, we call it a blazar. And in that case, we have a relatively steep boosting of the emission. Okay, so here's an example of the spectral energy distributions for some blazar. And they emit photons from a large range of the electromagnetic spectrum. As you can see, it has two peaks, where the first peak helps from synchrotron radiation from electrons traveling in the strong magnetic field at the base of the jets. And then the other peak comes from a positron known as synchrotron self-compton, where the synchrotron radiation is upscattered by the same electrons, giving this separate peak at higher energies that is directly correlated to the first peak. So if we observe maybe only the first peak and we can see where it is located, that can also tell us something about what kind of emission we expect from the blazar. So the higher the synchrotron peak, so the first peak, the higher the total emission. And we have observed local blazars to emit gamma rays well into the TeV range. For instance, Marcaria 421 and Marcaria 501 that have been observed at least 9 and 12 TeV, respectively. So we have good evidence of blazars being TeV sources. Okay. So, however, even though we have evidence of blazars being good TeV sources, we don't necessarily observe this TeV emission, and that is because the gamma rays are attenuated in something we call the extragalactic background light. So that consists of all the accumulated radiation from star-forming processes at active galactic nuclei. So basically, when the gamma rays they interact with the photons in the EBL, and they produce electropositive pulses. And this attenuation is accessible above a threshold that is inversely proportional to the redshift of the source and the photon energy, meaning that the more distant the source is, the less likely it is that you will see any TeV gamma rays. However, this may change if we have action-like particles. So action-like particles are a generalization of the axion, or the QC axion, which is the hypothetical particle that you get, or that it arose from solving the strong CP problem in QCD. However, an important difference between axion-like particles and axions is that axion-like particles, or ALPs, as I will call them from now on, do not necessarily solve the strong CP problem. They typically arise in theories where additional symmetries are broken, giving rise to pseudo-bosons. And one of the characteristics of ALPs is that they can mix with standard particles such as photons, electrons, and quarks. And in this project, we only look at the photon axion, or ALP. So we two new parameters, the axion, or ALP mass, and coupling to photons. So this mixing, this mixing gives us a way to look for astrophysical signatures of axion particles. So in the normal case, we have, as I said, that the gamma rays from blazars are attenuated in the EBL, and then the spectrum of received Earth, which is in K here in the turquoise line. So we just have the flux as a function of the energy, it's as severely suppressed at higher energies. You can see that it drops off pretty fast. However, if we have X-like particles that, well, actually, this is the mixing is described by Lagrangian here. And you can see that it depends on, or we have this B here, indicating that this only takes place in external magnetic fields. So in the magnetic fields of the jet, the photons can mix into X-like particles, and they travel unattenuated through the universe, and then when they enter the magnetic field of the Milky Way, they can mix back into photons. And so then you would have an expected flux at Earth that can look something like this. So you see that there's a very big difference in the expected flux at TeV energies, which part is here, but this is 1 TeV, that's not TeV, so here's in GeV. So there's almost no difference between the two at GeV energies and at TeV energies. The difference can be quite large. Okay. And so what we did here was to essentially calculate them for a range of different out models. What is the expected flux at Earth? And in order to find this, or the flux, so how many photons reach Earth, essentially depends on the magnetic field that the photons, the axions go through on the way from the source to us. And the main contributors are the jet magnetic fields, which is the strongest on the order of Gauss. And then also for sources that are part of a cluster, you also have an intercluster magnetic field, which is weaker, but it's also the distance is larger, so the photon has more time to convert into Alps, let's say. And so when the photon ray goes into the Milky Way magnetic field, it can, the axion goes into the Milky Way, it can reconvert into for this part of the project, we used the code called Gamma Ops diameter layer to calculate the peaking survival probability. Okay. So how do we use this to constrain out models? So as I said, we essentially produce plots like this for each point in the out parameter space. So this is just for example, an out loss of 5 for satisfying electron volts, and that both on them axion coupling of 4 times the parameter. And so we need something that can tell us, okay, what is the difference between, or whether the out model is excluded or not. So for that, we use the lock upper limit at 7 TeV. So so essentially we say that an out model is excluded when we have this scenario here. So blue is the lock upper limit, and then pink is the expected flux with Alps, and yellow is the expected flux without Alps. So if the expected flux with Alps is higher than the upper limit, then of course doesn't, and this out model is excluded. And I also want to show the plot on the left here, right, for PTS 1424, where you can see that the difference can be pretty large between the two fluxes, but if we don't have enough data, so the upper limit is above both of them, we can't really use this to constrain the upper window. Maybe in the future, this can be improved. Okay, so we use a total of 7 sources. After doing a stacked likelihood, we ended up with the following results. So this is our constraints in the out parameter space, where we have the out mass on the x-axis and the out photon coupling on the y-axis. And you can see though on this here how this compares to the current constraints. So we have our constraints in the other part. So not the most competitive, but it is also comparable to other gamma observers such as PES and Irving. And then in the future, with better data, maybe we can increase this vision. Okay. So for more details, this is the archive number of the paper, or Asmus. Okay. So for the next part of this talk, I want to go back to another effect that happens from what happens with these attenuated TeV photons and the electron positrons that are produced. So the electron positron pairs that were produced in attenuation are cascaded and essentially kind of they show up as a secondary GeV flux through this Prosnell's cascade. So the electron positron pairs inverse Compton scatter of the same extragalactic background light photons, which then produce higher energy photons, which then again are attenuated and produce new photons. And so the TeV photons show up as a secondary, or as a kind of bump of secondary GeV. Okay, so however, how we see this increased GeV flux depends on the strength of what is known as intergalactic magnetic field, so just magnetic fields in intergalactic space. So if the intergalactic magnetic field is very weak, below 10 to the minus 14 Gauss, then the electron-positron flares are only slightly deflected from the source, and you will see a kind of halo around the source of this Kerr halo of a GeV. However, if the intergalactic magnetic field is stronger, then the pairs are deflected more, and the GeV flux contributes to what is known as the isotropic gamma ray background. So we can't really say that, okay, this is from a specific source, which is in the background. And the isotropic gamma ray background consists of all photons outside of the Milky Way that cannot be attributed to any known source. It is constructed by taking the total extragalactic gamma ray background and then masking all known sources. It was shown in a recent work by Carlos Blanco and Tim Lindell that the IGRB can be almost entirely accounted for by contributions from aligned active galactic nuclei and star-forming activity, plus a contribution from undetected lasers. However, we want to calculate then what is the contribution from these cascades. We argue that. So, yeah, we got some pretty interesting results there. Okay, so before I show you the results, I just want to say a little bit about our methods. So we started by finding the intrinsic spectra of 1700 Fermi blazars. So that is all the Fermi blazars that have a defined redshift. And so the intrinsic spectra then means the spectra as it is actually from the blazar after we take into account attenuation, EVL, etc. And we use three different types of spectrum: power law, log parabola, or a power law with exponential cutoff. And then the cascades were calculated using the gamma cascade code by Carlos Blanco. And this part was also done by Carlos Blanco, one of our co-authors. Okay, so this is our main result. So in black here, you have the observed intrinsic isotropic gamma ray background as it is observed by Fermi. And then so the different wavelengths correspond to the expected IGRB with including cascades for a range of different cutoffs in the blazar intrinsic spectrum. So what we found is that we have to introduce the cutoff at 6 eV in the intrinsic spectrum in order for this to be within 1 sigma uncertainty of the observed Fermi-left IGRB. But as I argued before, we have pretty good evidence, I would say, that a lot of blazars, or at least a significant fraction of blazars, emit photons above this energy at 60. So we introduced this as a new tension that we need to solve in some way. So one possible standard physics solution to this that we looked at is beam plasma instabilities. So these are then instabilities that are created in the beam of electron-positrons as it travels through the intergalactic medium that can cool down the electron-positron pairs before this cascade cycle begins. However, this process is it's got a bit debated how effective it is. It depends a lot on the strength of the intergalactic magnetic field, the injection spectra of the beam, and so we find that for instance, it's very effective below an intergalactic magnetic field strength of 10 to minus 18. But in that case, you would also have these Kerr halos that we haven't observed. So we say that, okay, maybe this is an indication that the intergalactic magnetic field is feeble, because in that case, you can kind of solve this, that, okay, you have a certain parallels, but you also don't want to overproduce the RGRB. So we still have a potential here, I would say. One thing that we will be working on now is to see if there's any new physics that might solve this, such as axion-like particles, essentially kind of stealing away some of the energy in the RGRB. But yeah. Okay. So with that, I only need 2 short questions. So observations up to lasers can significantly constrain also out, and cascades from TeV lasers or produce the IGRB, which means that either lasers need strong spectral cuts, which are in tension with multiple laser observations, or the impedance will distance the field on bonds, or maybe there's some new physics that can solve this. Okay, thank you.